Okay. Hi, everyone. So my name is Jens. I work for the KVM and SV90 team at IBM. We've been trying out some things regarding many guests and many devices on a KVM hypervisor on SV90. And we ran into some things that we thought are interesting when doing that, and that's what I want to talk about today. So just like emus are usually living in small groups, I would expect that most of the time also QEMUs and guests are running on, a small number of QEMUs and guests are running on a host. So depending on how well it is equipped with resources, of course. So the point of this talk kind of is to show what happened when we try to make our QEMUs live in large flocks. And this picture down here is from the Wikipedia page of the Australian Great War on Emus from 1932. I won't tell the whole story now, but I encourage you to read up on it afterwards. I thought it was a really amusing read. It's basically about how emus were hunted by soldiers with machine guns mounted to their pickups, and about how the emus were just too intelligent and too robust and too fast for the soldiers to catch them. But let's get back to the talk. So what is this about? KVM runs on many devices. It runs on embedded devices, it runs on your laptop, it runs on larger servers, and it runs on the mainframe. I meant the mainframe. And we were curious to find out just what the limitations are of the libvirt QEMU KVM stack with respect to our systems. So the question was, how far can we go given a sufficient host configuration, and where and when does it break? So how many guests could we put on there? How many block and networking devices could we use? What resources are necessary in the host system? What configuration settings do you have to make, or do you have to adapt when you go move to more guests? And so I just want to point out that this was just testing the extreme limits. I'm not saying that you should run 4,000 guests on one host system, just because there's many reasons not to. I also won't talk about performance measurements, simply because I wasn't involved in them, and maybe there's not too much sense in doing performance measurements with 4,000 guests within one single partition. So we did run workloads, though. It was not just 4,000 idle processors. We did run workloads on a couple hundred of those guests, and I will talk more about that later. But let's talk about what we tested with. So this is the newest IBM mainframe model. And mainframes, you have to know, are always running a first-level hypervisor that basically just partitions the hardware. And we used one of these partitions to run a KVM host system. And this partition was assigned 2 terabytes of memory. It had 64 CPUs. They were shared with other partitions on the system, but most of the time after we were running just this partition, especially when running the test about many, many guests. And then as our guests, we were running both Rails 7.1 and SUSE 12. Guests had 1 gig of memory, 2 virtual CPUs. As the backend, we're using mostly image files as VirtIO block devices. Networking was bridge, but also vHostNet devices, VirtIO devices. So, well, this is what CPU info looks like. Now, what did we test? What kind of tests did we run? So we tested different things, not just many guests, but also attaching many block devices to a single guest, attaching even more Virtual block devices to several guests within one host, assigning quite a bit of Virtual net devices to a single guest. And then also, what also challenge was assigning large amounts of these resources to the host system itself, because it's not something that is done a lot. For example, in one test, we assigned 8 terabytes of RAM to the host. I'll talk more about that later. And we also tried to migrate many guests. I put 64 because it was our first test, but we could do just much more than 64. So, as I said, we did run into a few obstacles, and I'll start with a not very traumatic one. So, that is, when we did run into problems, so let's say we had a kernel crash and we wanted to take a memory dump. The thing is that the amount of memory in servers has increased much faster than the bandwidth to memory or to storage. So, and we have a special case here in S390. So in S390, we can do memory dumps in very early and late stages of booting. And when we do that, we're not using the typical KDump tool, but we have standalone tools that we install to separate disks and that we can boot when the system has crashed. So, not KDump, our own tools. And the downside of these tools is that you don't have all the features that KDump has. So there's no filtering, so no make dump file. You can only dump with one CPU at a time, and so on. So when you do these dumps, it can take a very long time, depending on how much memory you want to dump. So hours, days, depending on how the system is configured. There's a proof of concept that we're working on where we can use both KDump and our standalone tools in combination. And that works, it's just not widely deployed yet. So this is kind of work in progress. So this applies to both hosts crashes and guest crashes, but if you are debugging, want to take a memory dump of a guest, you could also just do a live debugging. And there's going to be a talk later this afternoon by David Hildenbrand. He will tell you all about how to debug KVM guests, and he will also go into that, I believe. So the next thing we did run into, and that's a S390 specific thing. On S390, so we're trying to create 2,000 networking interfaces in the host system. And the problem we found is that lies in the S390 networking driver code. So whenever you add a new network interface in Linux, the driver will rewrite all the current MAC addresses it's responsible for to the hardware, so it stores them in hardware again. And when you add a new one, it's not just going to add the new one, it's going to rewrite every single MAC address again, and then add the new one on top. And that took quite a long time. So even with 50 devices, it took more than a minute to add a new networking interface. So that's clearly a bug in our driver, and we're fixing this. But it was discovered just during these tests. Another thing that's probably obvious to many people is that the Linux bridging code is kind of limited to 1,024 ports. So if you need more, you would add more bridges, I guess. And then also just a system control setting, basically, that we had to increase is the number of IPv6 routing entries. So while we added these 2,000 devices, we had to increase that limit because it was also, I think, at 1,024. Okay, let's move from network interfaces to disks. We hit a few system control settings here as well, and I'm going to start with them because it's the most simple thing. iNotify watches, we ran out of them pretty quickly when we attached 4,000 disks to our host, so that's a setting you would increase if you want to use that number of disks. And then, of course, file descriptors. I'm pretty sure every one of you had to increase the setting of maximum file descriptors at some point. So did we in this case. And so let's count file descriptor usage in QEMU. Just by an example. I looked at it, and most of the file descriptors we use are event file descriptors. We have one per word queue. So let's look at an example of a VirtualNet device. We have one word queue for send and receive. Probably more if you use multi-queue, I guess. One for a control lane, kind of. Then for def vtap, def vhostnet plus 3 IRQFD. So that's 8 file descriptors in total. Do that for 1,000 VirtualNet devices, and it goes boom. And that's just because our default setting was too low. But the bottom line is that we need many of them. So just be aware of that if you use many devices. It's the same for block devices, of course. It's just that they use less word queues. So let's see what happened when we used many virtual block devices in a single guest. We started with one, added some more, still fine, added a lot more. And at that point, we discovered something interesting. So we tweaked all the system control settings now, and what could still go wrong, right? And before I go on, I have to say we tried this a while ago, a long time ago, and back then we were still using select, but now we're using poll. So back then the limit was at 1,024 file descriptors. So, but now our target was 4,000 disks, and we started with 1,000. And what we noticed when we did that, our guest took 13 minutes, sometimes more, sometimes a little bit less, to start up. And so one of our developers debugged into it and found a problem. Actually, it was a regression that had sneaked in a while ago. And so what the problem was that we were calling this function block drive train all for each single VirtIO reset and for every block driver state. That's a lot of calls to our poll. And the problem is that actually we don't have to call that for every single block driver state. We can call it for every single AO context, and that's just fine. So with this fix, we got down to 16 seconds for 1,000 disks. And, well, this is the upstream commit. So we could even use the 4,000 disks. After that fix, there was no problem, really. Okay, more disks, but not within a single guest, but with over multiple guests within one host system. And now the first thing we had to tweak was the setting for the maximum number of AO contexts. Just a syscontrol setting, and with that fixed, there was no further problem actually here. So that worked quite well. Now let's move on to starting many guests. Remember, our guest had a VirtIO net interface, VirtIO block disk backed by an image, and 2 virtual CPUs. So then we continued to add more guests. Everything fine, everything fine, everything fine. At some point, it was not fine. And again, let me start with some of the settings that we had to tweak. I know if you run into these things at some point, it's obvious, oh, of course I have to increase that, but in some cases it took us a little bit to find that out. So the first thing, again, was open file descriptors. And I guess that's too small to read. So there's a setting in libvirt config file. You can increase that there, and it will increase the maximum number of file descriptors for your libvirt daemon process. Then max PTYs. We ran out of them as well. But there's a syscontrol setting. You just increase it. And it goes on. It scales quite well. When you start many guests, you also create many processes and threads. And they can be limited too. So in the beginning, our whole system, we just had to increase this number in the libvirt daemon file. And libvirt different service, actually. That will increase the number of maximum processes for your libvirt daemon process. And then if you need to increase this number for individual QEMU process, there's a different config file or a different setting in qemu.conf. So we did that as well. And then the most simple problem, actually, when we started this, we just didn't have enough RAM. I think we only had a terabyte or so. Too bad. So we added one more to 2. And with that, you would think, OK, now we got it all. Let's start guests. But then I learned something new that day. So it turns out, and before we were using an internal distribution that wasn't using systemd, and I just didn't know, but there's a service called a static service called systemd machined. And so libvirt will call this function in this machined via an RPC over dbus every single time it starts a guest. And the problem was here, actually let me go back one. So at some point, we're starting guests after guest after guest after guest. And actually, even at something like 20 guests plus or so, we would see hangs. So we're starting guests in loop, and it would start, and it would just hang, do nothing anymore until sometimes a couple seconds later, sometimes a few more minutes later, it would go on. And we just didn't know why. And we looked into libvirt code and everything and debugged for quite a while. But then, given this error messages, I eventually tried to find what this create machine function was that was called here. And that was in the systemd machined service. So turns out that in older versions of systemd, this message handling that they were doing there in their message loop was kind of buggy. What they're doing were read all messages and handle them, and then go one step further. But in this next step, there was what nobody noticed was they would read again messages from that file descriptor or from that dbus socket or whatever. And then the next step was, OK, wait for more messages. And so at this point, it was just sitting there and waiting for more messages. And it would only continue, the loop would only continue when another guest was being started. So at that point, it would go on and process all the messages that were read previously into the buffer. Yeah, that was buggy message handling. That's fixed now. So first thing I found was a patch that someone attached to a CentOS Bugzilla that would fix this message handling. And I tried it, and with that, it worked. We could start guests. So this fix went into systemd version 2.19. I'm not sure. I don't think they attached a patch that was originally developed for it, but they rewrote the entire message handling loop. But with this rewrite, we were able to start 4,096 guests. And I can't do a demo today, but I took a couple of screenshots. I hope that's OK. So at this point, when I took that screenshot, we were close to running 4,000 guests. You see there's quite a lot of tasks, but only 24 running. So go into that right now, a little bit later. So you see that we defined way more than 4,096 guests. We had defined more than 8,000, in fact. And at this point, we were close to 4,000, actually. And so given enough resources, this was absolutely possible. And the system was absolutely usable. It was stable. You could still do everything. wasn't sluggish or anything at all. So yeah, this is also a screenshot of output of 3. So we weren't using all the 2 terabytes. And the workloads that were running, I mentioned at the beginning, we didn't run workload on all the 4,000 guests. I think we're running workload on close to 1,000. It was a CPU stress tool and networking stress tool. I think there were some instances with block I/O stress. Yeah. So this is a screenshot of a guest actually running this unheard tool that's stressing the CPU. Yeah. So there were quite a few of those as well. And I think for networking stress and so on, we used the stress tool itself and others. Okay. I'm not sure if I skip over this. Well, okay, let's go into it. It's a little bit exotic, so I thought why. Not sure I wanted to talk about this. But in QEMU, we use many threads and do that for vCPU threads, I/O threads, and so on. And gRPC has had for a while this thing called per-thread memory pools or arenas. And these arenas are created per thread. And so they just allocate some address space, basically. So for example, the maximum number of these arenas is calculated by, or is limited by the number of cores. So on a 64-bit system, we have 8 memory pools per core maximum, times 64 megabytes of size that each of these arenas has. So with 64 cores, as in our case, that would be 512 arenas, which is 32 gigabytes of address space. And that's a lot of address space, which is usually not a problem, right? But some people use strict overcommit. And then all of this is accounted a little differently. So malloc will fail earlier on you, and you will get a bad return code and so on. This would get worse if you increase the number of cores, because then you have kind of more arenas. You can cap the setting by setting an environment variable to a smaller number. So in our case, with this set to 16, it worked quite well. Now, I'll admit that this is kind of a niche problem, because many people will say, why would you use strict overcommit? But some people do, and for them, they have to be aware of this. So even though not many people will use this, I guess, this is still a thing. Okay, let's talk about migration. And here I have to say that we didn't really have much problems. Just 2 little things. What we did run out of first was ports. So you can have a default setting, there is a default setting of 64 ports in the libvirt config. And if you want to do more concurrent migrations at a time, you would have to increase that setting or just specify the port directly, I think. So no big trouble so far. Then another, I guess, strange thing was that one of our testers was using scripts that he ran from another host to trigger on our hypervisor here. And at some point, these scripts will also get stuck. And that was just because he was running out of SSH sessions. So you can only, by default, you could have 10 sessions at a time. But increasing this number, it worked also quite well. Okay, so now I'm almost nearing the end of my presentation, but I have a few things where actual code was setting limits. And we're starting with something that only affects S390 again. So in QEMU or in KVM, there's this define for the maximum number of pages, and that means that we can only have 8 terabyte per mem slot. So now for S390, we only have 1 mem slot for our system RAM. That means we would probably move to something that uses more mem slots. And I think that x86 already does that. I'm not sure. But to put this into relation, right now the newest mainframe model can have 10 terabyte for the entire system. So I admit that it might not be a real problem right now, but future mainframes will have a multiple of this. So who knows? So this was not the only 8 terabyte limit we found. And this was just a simple bug in our S390 management code. The problem was that the return code of a memory management-related function was an int where it should have been something bigger, an unsigned wrong or something. And with this fix by Martin, we could successfully assign more than 8 terabyte to our host system, and it would start up and be usable. But let's get to something more specific. Our in-kernel IRQ chip, setting up routes. So we create an S390 again. We create a new IRQFD per word queue. And every time a new IRQFD is created, we reallocate. So in the kernel, what happens then when we do this IO control? The entire routing table is reallocated and repopulated. And with many devices that have also many word queues, this will cause delays. Because the problem here was that in our S390 code, in QEMU, for every new route, we would call this IO control. But the interface actually allows that you can first write all the routing entries to a global table within QEMU, and then just commit all the routes to the kernel by calling this KVM set GSI routing call. So we weren't doing that, but fixed this, and kernel was the patch was sent upstream. I think it was already added, or maybe not. But and I was talking about this like it's only specific to S390, but I think Paulo also wanted to look at the x86 or PCI-related functions that might do this similarly. Okay, then another thing with the IRQ chip is that it has pins, and they are defined, they're not limited, but they are defined to be 1024. So for S390, we already extended that to 4096. And again, S390 is a special case here because we were asked, or we had to integrate with the already existing concept of the IRQ chip and routing entries, which doesn't quite fit our adapter interrupt concept we have in S390. The problem is that for each word queue, we set up an IRQFD. And we do that to create a mapping between the word queue and our adapter interrupt indicator bits and summary indicator bits. So we have a summary indicator field here, that's a large bit field, and each bit is indicating an adapter that we want to inject an interrupt for. Now this interface requires us to add a routing entry for every word queue, but we're thinking about how we could do that differently. So of course we could just go on and bump up the number of pins forever, I guess. Or we could like to change the interface, or I hope we don't have to create a new one or something, to support a payload where we can just, and the payload would be just an integer basically, which is an offset to our summary indicators. With that, we would not have to set up so many routes. And I think that was my last slide. Coming to a short conclusion, and I would like to say that we did not find many things that are fundamentally wrong and that would prevent a user from running many guests. Simply because I think KVM is already in quite a good shape regarding scalability. I do think it was worth doing this effort here because, one, we learned a lot, and I'm now able to share this here. We did fix a few things, and we have some things to think about now. So, as I said in the beginning, I won't recommend running 4,000 guests on your host, just because that depends on so many things, and we have more than one partition that you can use. So, but it's nice to know that this number is not completely out of this world. So that being said, thank you, and I'm open for questions, I guess.
I'm curious that whether you have done any comparison between when you have many disks in a system and many guests with many disks in a system compared to when you have only one disk, for example, and how does the performance look like?
Okay. Well, as I said in the beginning, we did not, or I did not really look into, we didn't run a full performance test. I can say what I know from my colleagues who've done these things. They haven't done performance tests with 4,000 disks, but they have done performance tests with many disks. And compared to our other solutions with our other hypervisor and so on, we look quite good. Numbers are really good, especially since we have data plane. That really bumped us up quite a bit.
Oh, okay, thank you. I'd just like to mention that because I'm working on improving the event loops, and so that we don't need to create one IO thread per device, so we can limit the number of total threads inside of one VM, which means we need to do some work around the pooling syscall and making use of the ePool interface of Linux, or make the AIO interface more efficient. So, by the way, I'd like to mention that there is also a talk about this during Friday afternoon, and if you are interested in that, you are very welcome to come and discuss stuff.
Okay, sounds great. Yeah.
Thank you.
Okay. Any other questions? If not, then thank you very much.